Wanted to work through an example that involves two-slit interference. The two-slit experiment was a very famous experiment. It was conducted roughly 200 years ago, and it demonstrated unequivocally that light has wave properties, because it demonstrated the interference of light, constructive, destructive interference of light, which is a wave-like property. So in this question, we're asked to imagine a two-slit setup, and we're actually going to think about several two-slit setups. One in which we create an interference pattern with sound waves, one where we create an interference pattern with microwaves, and then finally one where we create an interference pattern with light waves. So the sound, the microwaves, the light waves are all waves. They all exhibit constructive, destructive interference, and they will all show in appropriate two-slit experiments with those waves, bright fringes, dark fringes, constructive, destructive interference. So the question says we've got 17.7 centimeter wavelength sound waves, and they impinge on the two slits of a two-slit experiment, and the slits have a separation of 30 centimeters. The first question is find the angle of the first minimum. And so this is a question about sound waves. So the basic equation for the location of the bright fringes in the two-slit experiment, the direction, the angle of the bright fringes in the two-slit experiment is that d sine theta equals m lambda. In this equation, d is the slit separation. I've pictured it over here on the two-slit experiment. Theta is the angle with respect to the axis of the two-slit experiment, the angle at which a bright or a dark fringe, constructive, destructive interference occurs. And then lambda is the frequency of the sound or the microwaves or the light waves. And m is the order of the bright fringes. So in this case, m equals 0, that's a central maximum that occurs at 0 degrees. M equals plus or minus 1, they're the first maxima to the left and right, or upstairs and downstairs of the central maxima. And then there would be other maximas, plus or minus 2, plus or minus 3, and so on. Now, in this particular case, we're asked to think about the m equals 1 maximum. So the equation that we're going to go ahead and use is d sine theta equals lambda for the m equals 1 maximum, the direction of the m equals 1 maximum. And we're asked to figure out the angle, so we've got to just rearrange this. Sine theta will be lambda divided by d, the wavelength divided by the separation between the slits. And dividing the wavelength, 17.7 centimeters, by the slit separation, 30 centimeters, I got a value that is 0.59. And if I take the inverse sine, the arc sine of 0.59, I get the angle itself. And the angle in degrees came out to be 36.2 degrees. And so that's the answer to part A. The direction of the first maximum, the maxima that are immediately either side of the central maxima, for the case of the sound waves on the 30 centimeter slit separation. So part B asks us to now think not of sound waves, but microwaves. And it says, what slit separation would be required if you had 3 centimeter microwaves instead of the 17.7 centimeter sound waves, and you wanted to have the first maximum at exactly the same location for the sound and microwaves. So again, in this question, we're going to use this relationship for the first order maximum between the slit separation, the angle theta, the direction of the maximum, and the wavelength. In the last case, we knew the slit separation, we knew the wavelength, we wanted the angle. In this particular case, we actually, I'll write down the equation again. We want the slit separation, knowing the wavelength and knowing. So if I rearrange this equation for the slit separation, D is going to be equal to the wavelength of, in this case, microwaves, divided by the direction, sine of the direction to the first maximum. We know both these. We know that the microwaves have a wavelength that is 3 centimeters. We know that the sine of the angle was 0.459. And dividing one by the other, I get 5.1 centimeters for the slit separation in the microwave experiment. Finally, in part C, we're asked to imagine doing the same experiment again, but this time not for sound waves, not for microwaves, but for light waves. And we're told that in this case, the slit separation is now 1 micrometer, so 1 times 10 to the minus 6 meters. And we've got the m equals 1 maximum at the same location as the microwave experiment and the sound wave experiment. And we've got to figure out the wavelength of light this time that corresponds to the maximum being at the same location. So let me write down this tired old formula one more time. This relationship between the slit separation, the angle theta of the maximum, and the wavelength of the waves. And in this case, if we look at this equation, we know the slit separation, we know the direction for the first maximum. The only thing we don't know is the wavelength of the light. And so this time we're actually solving for lambda. And if we rearrange, not even rearrange actually, if we just fill in the separation between the slits in this experiment, so that's 1 times 10 to the minus 6 meters, the sine of the angle towards the first maximum, that's 0.59. We can calculate the wavelength of the light, and I got a value that is 440 nanometers, 0.44 microns. Well, that problem about the two-slit experiment was all about the first maximum of the two-slit experiment, which is a special case, if you think about it, of this equation here that tells us all of the maxima from the central through the first to the second, third, and so on and so forth. It involved thinking about that relationship between the slit separation for the two-slit experiment, the direction of the maximum, primary maximum in the two-slit experiment, and the wavelength of the waves. And it asked us to do that for 3 types of waves: sound waves, microwaves, and light waves. So in one case, in part A, we knew the slit separation and we knew also the wavelength, and we figured the angle theta. In the second part of the problem, that's the microwave part, we knew the angle theta. We also knew the wavelength of the microwaves, and we solved for the slit separation. And then finally, in the third part, we knew the angle theta, we knew the slit separation, and we were solving for the wavelength. And so that's kind of walked us through different ways that you can employ or use that equation that describes the maxima in the two-slit experiment.